Here is the next example. In this example, it's, don't be scared after looking at the diagram. It's a basically three-phase circuit. It's kind of hard to look at the circuit or find out which one is, what is the connection of the source, what kind of connection is the load. So what I'm going to do here, I'm going to redraw the circuit diagram. So here is my A, B, C. It's look like a Y connection on the source side. When it comes to load side, here is my A. Remember, B must be connected to B, so my B is going to be here. I'm following clockwise on the source side, but when it comes to the load side, I'm kind of following anti-clockwise. Okay, but to avoid confusion, I'm going to redraw the circuit. So here is my source, A, B, C, and this is going to be grounded. Now here we have some line impedance, which is 1 minus J1. Now A, B, C, it's look like a delta. So what I'm going to do, I'm going to draw a delta load here. Okay, so A, B, C. So B has line impedance and C has line impedance. Okay, so here this is 15 plus J12. This is 1 minus J1, 1 minus J1. Okay, the voltage here, he clearly mentioned that's a phase value. So basically, I'm going to take that as a phase voltage 120 at an angle of 0. Okay. Now, in this case, I have a line impedance. I don't know how much the voltage drop across the line. Okay. You can use the nodal analysis or mesh analysis to solve without transferring the circuit. But what I'm going to do, I'm going to transfer circuit, the load. I'm going to transfer this load, it's a delta load. I'm going to transfer that into a Y load. Let me explain how to do that. So here the delta load, we know the delta values, which is ZAB, so ABC, so impedance between AB is ZAB, BC and CA. Now I'm transferring this delta into a Y. So basically what I'm doing here, I'm transferring this, so I need to find the ZA right there. Now to find ZA equal to, ZA is surrounded by AB and CA, right? So multiply those two, ZAB times ZCA over ZAB plus ZBC plus GCA. I'm adding all these three. Okay, so that's how we'll find the impedance A across A. And you can see the remaining ZB equal to, so B is right there, so surrounded by these two, AB and BC. So ZAB times ZBC over all three, AB plus BC plus CA. Same thing with ZC equal to ZCA times BC over AB plus BC plus CA. Okay, now if we have a balanced load, that's going to make it easier our life, because if you have a balanced load, then what happens here, all these three quantities are same, right? So basically ZA equal to, I'm going to take the same number 3C, so it's going to be Z over 3. So when you're transferring a delta load into a star load, if it is a balanced, all we need to do is just divide it by 3, ZAB over 3. That's what I'm going to do. So I'm going to transfer this delta into a Y load. So when I transfer this into a Y load, this is what my load is going to be look like. I'm going to eliminate those red lines in a second. Okay, so this value must be, there you go. So this value must be 15 plus j12 over 3, which is 5 plus j4. Okay, 15 divided by 3 plus j12 divided by 3, 5 plus j4. That's a, now what I did, I converted a delta load into a star load. From here, solving this example is similar to the previous example. So what is the load power factor? Let me write down load power factor. So the first thing we can do, we can find the load power factor equal to RL over ZL. RL is 5 ohms, ZL is square root of, we have 5 square plus 4 square. That value is 6.4, so it is 0.78 lagging. That's the load power factor. Now to find the source power factor, similar to the previous example, what I'm going to do, I'm going to, since it's a balanced load, I'll find a single phase. I will separate a single phase source and then solve it for single phase and then multiply by 3. So that way I will end up finding all the quantities for 3 phase. So here I know it's 120, this is 1 minus j1, 1 plus j1. Okay, now what is the z total? Z total must be, sorry, this is 5 plus j4. Z total 5 plus 1, 6, j4 minus j1 minus plus j3. That's the total impedance. Okay, so source PF equal to 6R over Z, 6 over square root of 6 square plus 3 square. Or you can find the theta value or convert this into polar format, whatever the theta, you can say cos theta equal to the power factor. Okay, so that value is 6.9. The power factor is 0.89 lagging. So it's a YY connection basically. So in YY connection, what I can do, I can find line current is same as the phase current on both sides, phase and load, which is 120 divided by 6 plus j3. That value is 120 divided by, so that value is 120 divided by 6.7 at an angle of 27.12, which is 17.91 at an angle of minus 27.12. So now I can find power supplied by the source. I'm not finding power consumed by the load because if it is, let me write down PL equal to 3 times VPH IPH cos theta, right? Cos theta L. Now if you look at the load side, I know the voltage across the source side. I don't know the voltage here because out of 120 volts there will be some voltage drop across this line because the line impedance. That is the reason I'm unable to use this formula because I don't know this value. I don't know that. Okay, so that's the reason instead of PL I'm going to find P source because I know the source voltage 3 times VPH IPH cos theta source. I know every value here, so 3 times VPH is 120, IPH is 17.91, cos theta is 0.89. That value is 5.74 kilowatt. I converted into kilowatt. Okay, same thing, Q source must be 3 times VPH IPH sin theta s. You need to find the sin theta s from the cos theta s. 3 times 120 times 17.91 times, so sin theta s is 0.455, so I end up with 2.93 kilovolt ampere reactive. That's the reactive power supplied by the source. Now I can find SS, which is PS plus J QS. Why plus J? Because the total, when you look at the total impedance, I have plus J3, so it's still a inductive reactance. So inductive reactance always takes the reactive power, so that's the reason it is plus JQS. Okay, so which is 5.71 plus J 2.93 kVA, okay, kilovolt ampere. Once you have SS, if you want to find S source or apparent power, which is 5.71 square plus 2.93 square, that will be 6.417 kVA. So these are the source quantities. Now he's also asking about the load quantities. So when it comes to the load quantities, what I'm going to do, since I already know source quantities, I'm going to find the losses in the line. So P line losses, equal to 3 times what is the current flowing in the line, which is IL square times R line. Okay, so 3 times what is the current flowing in the line, 17.91, because it's star, that value is same, phase current. So this total power equal to 968.76 watt. That's the power loss. And same thing with Q line losses. Why I'm saying losses? Because whatever we are supplying power here, whatever power consumed in this line, it is, we are wasting it. So that's the reason we are calling that as a loss. So Q loss is equal to 3 times IL square X line. So it's going to be 968.76 VAR. By the way, here I have capacitive reactance. So capacitive reactance does not consume reactive power. It always supplies the reactive power. Okay, so it supplies the reactive power. So basically this value must be negative, since capacitive reactance supplying the reactive power. Okay, since capacitor is supplying reactive power, that's a minus. So what is the P load? P load must be P source minus P losses. So P source I have 5.71 minus losses I have 0.68, I can 0.97. That will be 4.74 kilowatt. And same thing, Q load, Q source minus Q losses, but remember the line is not losing reactive power, basically it is supplying, so it's minus of minus. So 2.93 minus of minus 0.97, that value is 3.9 kVAR. Okay, from here you can find S load equal to 4.74 plus J 3.9 kVA. Okay, that's the final answer. Now what I'm going to do, I'm going to draw the vector diagram for this circuit. So what kind of load is this? Usually whenever you draw the vector diagram, we will draw the vector diagram for the load. Okay, so can you guys tell me what is the load current here? This IL must be, I know this current, because current flowing here is same as the current flowing there. That value is 17 point something, right? 17.91. This current is 17.91 ampere. What is the current passing through this? This must be this is a delta load. So in delta load current, so it's nothing but phase current. Basically the phase current equal to load current, line current divided by square root 3. That value is 10.34 at an angle of, the angle here depends upon this, the load impedance. So I can find, we already have cos theta L, which is the load power factor we just found, which is 0.78. Okay, so this must be 0.78. So theta L must be cos inverse of 0.78. Cos inverse of 0.78 equal to 38.73. Since it's a inductive load, it must be negative angle there. I mean, for the current always lagging, right? Minus 38.73 degrees. So IPH equal to 10.34 at an angle of minus 38.73. So when we draw the vector diagram, we always draw for the phase quantities. So phase A, that's a IA. This is at minus 38.73 degrees. Okay, IB and IC. This must be 120, 120, 120. Okay. Now your VA must be, here is my VA, VAN. Okay, and since I know IA, my line current is going to be somewhere here. This is negative IC. This is my IA I line. Okay, this angle is always 30 degrees. This is the vector diagram for the given circuit. I will stop this video here. In future videos, I'll solve more examples on delta Y and delta delta loads. Thank you.